Thank you very much. It's great to be here, and it's really quite amazing to see so many people here for the conference. So congratulations to Mark and to Robert for putting on such a great event. So I'm actually here today to talk to you about an open source project, and it's an open source project that we started together between Barefoot and Google a little while ago, and more recently with the Open Networking Foundation. Many of you may have seen a demo of this, the P4 runtime API, over the last few days. If you had a chance, there's a demo running downstairs. So the basic idea of P4 runtime is to finally put the control plane in charge of the forwarding plane. It seems like, isn't that what a control plane does? Well, if you think about it, that isn't really how it works. I want to explain what the problem is today and what we're trying to do to fix that. The basic idea is to make sure that the APIs that we use between the control plane and the forwarding plane are able to not only tell the forwarding plane what to do, but to be able to extend that behavior so that it can perform any packet processing that the control program would like it to do. So let me start with a simple picture. This is a cartoon picture of pretty much any switch or router that you might find. It has a Linux-based switch operating system at the top, and then an ASIC for processing packets at the bottom. Protocols and features are implemented as user-level processes above the switch operating system, and then there's an API that those protocols use to control the switching chip underneath. Today, this is pretty much how all network switches and routers are designed, whether it's from a networking equipment company or from a large web-scale company. So in the past, this API, and in fact still today in many cases, this API is closed. It's fixed. It's proprietary. It's available only under a very onerous NDA. So why is that? Well, to be generous, one could say, traditionally, the switch chip has been fixed. We've known pretty much what protocols people wanted to use, so they get baked into hardware. So is that the cause or is that the effect? It's actually hard to tell, because we've gone down that path, and so they are fixed, and so we end up with fixed APIs. That tells us why they're fixed. It doesn't tell us why they're locked down and locked in. Well, that's a competitive strategy, and we all know that basically if you can prevent your customers from sharing an API with anybody else, then they can't use another chip, and nobody else can mirror or have that same API. And it causes a stifling of competition, a stifling of innovation. And you can look around our networking industry and you can see the effects and the bad consequences of that. So we've all known that for a while, and so there have been many attempts to try and change this model. One attempt that many of you will be familiar with is OpenFlow, shown in this picture here. So OpenFlow was designed back in about 2007 in order for one control plane to control a number of different switches from different switch vendors. OpenFlow tried to exploit the fact that the switching ASICs were fixed and all did pretty much the same kind of thing to define a way of specifying the matches that you would perform and the API that you would use to communicate with it. So for example, you might say, I'm going to use Ethernet, IPv4, ACLs, etc. And so these are the fields that I would use. So the main goal was for OpenFlow to be able to express from a control plane to a forwarding plane how to populate the tables, what entries to add, what entries to delete, what entries to modify. And we can see that it was pretty successful because nowadays many data centers and increasingly service providers are developing control planes themselves or using open source control planes or commissioning, writing, modifying control planes that leverage that open interface to the data plane. So while OpenFlow has been open, it is also fixed. Now you may look at it and say, hasn't it changed over time? But it's been a painful process. It started out with about 4 or 5 different protocols, and now it's up to about 45. But when you look at it, you can see that it wasn't designed to be extensible, and it's been a painful process as it's gone along. Worse, OpenFlow, and this is with hindsight a mistake, It specifies the fields upon which you match. It doesn't specify the action that you then take following the match. And different switch ASICs, different vendors, implement them in different ways. Why is that? Because standards are ambiguous. We all know that. They're written in English. And so different switch ASICs have to be, a huge amount of effort and money goes into testing for that interoperability to see whether they can be made to interoperate. So unfortunately, OpenFlow is fixed, and its specification of the behavior is ambiguous. SAI, SAI, or the switch abstraction interface was developed with a very similar goal in mind. In the case of SAI, it was designed for when the control plane, instead of being remote, was present on the same switch, or same box as the switching ASIC. It was designed to work with a number of different types of switching ASIC, and in fact, it has been deployed in that manner, and so that's good. It's open, and it's silicon independent, but it itself, again, is fixed. And for anyone that's taken a close look at it, you can see that it's growing, and so it's going to encounter the same problem, which is it's going to be very hard to extend over time. So what to do? Well, a number of us took a step back and said, what would you do if instead of working with fixed switch ASICs, where the behavior is defined from the bottom up, they tell you via a datasheet what they're going to do, what if instead you could tell the switch ASIC how to process packets? Then you need an API that is extensible. And in fact, it may be better not to think about it as an API anymore. It's just merely a way of adding and deleting table entries according to the way that you've programmed the chip. So the challenge that we set ourselves was, can we design an open, silicon-independent API that is easily enhanced as we evolve the forwarding plane, and one that can be used equally for a remote control plane or a local control plane that's on the box. So fortunately, there are two things that are happening at the same time that kind of make this a little bit easier. The first one is the emergence of the P4 language. I'm sure many of you have heard about it. This lets us describe the way in which we want packets to be processed. In other words, instead of the switch telling us, we tell it how we want it to process packets in an unambiguous fashion. The second thing is P4 programmable switch chips. The PISA architecture, which I'll describe in a moment, and Barefoot's Tofino switch chip have moved down in this direction, as many of you know. But actually, we can expect there to be more P4 programmable switch chips to emerge in the next few years. So P4. P4 language was originally written by a number of different organizations, Google, Intel, Microsoft, Princeton, Stanford, Barefoot. And over time, it's grown into about 70 different companies. And there are many people that are actively involved in defining the language, creating tools, compilers, debuggers, and contributing P4 programs to the community. The important thing is it's Apache licensed. It's designed by a group of people from many companies. The attempt here is to create a truly open ecosystem for the benefit of industry as a whole. It's independent. The board that governs p4.org includes someone from Google, someone from Princeton, and myself. And we welcome and invite anybody here, whether you're at a chip vendor, an equipment vendor, an operator. We all benefit from an open ecosystem. So if we can work together on this, we will benefit greatly as an industry. I want to explain a little bit about how P4 works, and I'm going to do it in the context of this particular forwarding paradigm. It just makes it easier to describe the behavior if I do it on the PISA or protocol-independent switch architecture. It's not defined or constrained by this architecture. It just makes it a little easier this way. So in the PISA architecture, we define the behavior of the parser on the left-hand side, which will then take the headers and the header fields and then have them processed by each stage. Each of these stages is identical and initially unprogrammed. It doesn't know what a protocol is. The fields will match on the little blue boxes, the memories. That's the match stage. And the ALU represents the action. Many of these can happen in parallel on one packet header, and then in series because of possible serial dependencies in the program. So let me just show you by way of very trivial cartoon example. Here is a packet arriving with different colored packet headers at the beginning. The parser, under our control, under our description, will then break apart those fields and put them and present them to the first stage. Many of them could be processed in parallel by the different the memories shown in blue here. And that will then process it, and you can think of it as mapping that to a new set of headers. Many of them will be unchanged. Some of them may be modified. A TTL could be decremented, a new header could be encapsulated, another one could be popped, a new label could be added, etc. So that set of headers will change as it goes down this pipeline according to the program. The reason that we'd have multiple stages, so you've got multiple sequences of processing, if there are serial dependencies in the way that the packets need to be processed. Eventually, at the other end, it will reach a set of headers that we want to depart. They will be placed into the packet, and then it will be sent on its way. Here's an example of a P4 program. In the middle is the description of the headers. It's like a C-like syntax that merely says here, this is what an Ethernet header looks like, this is what a VLAN header looks like, etc. Be very familiar to anyone that's familiar with networking. We have the parser, and we do that just by merely describing what the headers are, rather than an operation of how you process it. You just say, this is what they are, and this is where the fields are that distinguish one header from another. And then finally, we need to describe the tables that are in the different stages that says, this is what an IPv4 header looks like, table looks like, this is how you match upon it, whether you're doing a longest prefix match or some other kind of lookup. These are the actions that you would perform, like decrementing a TTL, updating a checksum, encapsulating a new MAC header. That would be the action portion of it. And if you wanted to define a new table and a new instruction and a new header, that's where you would define it in this program. Finally, you need a control flow, which is in the blue on the right, that tells the chip how a packet will progress through the chip. So essentially, you're defining a very, very broad type of pipeline where you can describe that pipeline behavior however you need for your environment. One example of this is the Barefoot Tofino chip. I'm not going to dwell on this too much, but just to say there is an existence proof of this already. It's programmed in P4. It's the world's fastest switch chip. Its behavior is defined in P4 by the user. And one interesting fact is that if you write a program and it compiles, it will always run at line rate. And if you look at the previous graph, it should be pretty clear why that is. It's a feed-forward architecture, and there are no separate CPUs or et cetera inside the device. So apart from being fast, one thing that we've observed, and I take this as an existence proof, the cost and the power are the same as fixed function chips. This is something that didn't used to be true. The area is identical. The power is identical. The performance is the same or slightly higher. What we've discovered is that P4 is a very easy language to learn. I've observed people, whether they're undergraduates or experienced engineers, they've heard about P4 in the morning, they've written programs at lunchtime, and committed them to the repository in the afternoon. And I've seen this happen several times, from all across the industry or people that have never seen it before. This is a very, very easy to use language. And as I say, if it compiles, it will always run at line rate, so it's very easy to get systems that work. Really, the problem is this. The problem is this, that we've been operating under this tyranny, and we've had sort of blinkers on, in my opinion, in which the behavior of networking equipment has been defined by data sheets. It's been defined from below for us. We are at odds with the rest of the industry in this. We are behind. So what happens is, there is a data sheet written usually in an ambiguous English form that tells us how our system will work, and we have to live with it. If we want to change one of those features, it typically takes 4 years to add a new feature. It's not surprising that it's a problem. Take VXLAN, defined in 2009, first deployed 2014. The rest of our industry, whether it's GPUs, signal processing, machine learning, has moved away from this model. They've moved to one in which software developers define their behavior. If they've got new ideas, they write new programs. And when they've got new ideas and new programs, you get this Cambrian explosion of new ideas. That's what innovation is. And from those programs, they compile them down from a definition of a behavior that they would like to have happen and tell a switch what to do. So today, not only for the Tofino switch, you can do this with devices from Xilinx. You can do it from the Netronome SmartNIC. You can even do it with OpenVSwitch to tell it how to process packets in the kernel derived from a P4 program. The same one would work on all of them. Just like I do on my computer, in fact. So this is the experience that we're hoping that people will get. So it kind of begs the question, does this change us from vendor-driven to user-driven? That would be nice. We're a bit of a laggard in our industry for not having done that already. So why aren't all networking systems built this way? So programmable switches we've been told for years and years, are 10 to 100 times slower and more power hungry and cost more than the conventional fixed function switch ASICs. I can tell you categorically, this is not true. And the existence proof of Tofino tells you that's not true. There is no magic in that chip. There will be many more, many others that will do the same. And I would predict that within 5 years, every reasonable switching chip will be programmable. It may or may not be P4. Let's work together to try and make it so. But they will be programmable in future. If you want to play around with them, there are a few ODMs that make 6.5, 3.2, 1.8 flavors of these. There are a number of coming soon. And within the next few months, you'll see at least 7 networking equipment vendors coming out with boxes based on this. OK, all very well. Nick tells you that you can program your switch chips. What are you going to do with that? What are you going to program it to do? Let me just tell you some examples of what we've seen so far. The first usage that we saw was rather than to increase the complexity that you may be fearing, it was actually to reduce complexity. This is probably the most common case. Why would someone do that? Some people like to write their own P4 programs. We saw an example downstairs of Tor.P4, fresh written P4 program. Others will say, actually, I want to reuse and pick and choose amongst protocols that I have. Why don't you give me one that exists already? So there is a program called switch.p4 that has this set of features. They're all the features that you would expect to see in a wide variety of networking equipment and fixed function switch ASICs today. So there is a program, switch.p4, that's 4,000 lines of P4. It's open source, you can have it. And from that, you can simply decide which ones that you want. Now, some people get greedy and say, hey, I want all of them. Actually, I'm yet to see anybody that does that. What they do is they say, hell, I don't use 90% of these protocols. Different people want to use different ones. So they pick and choose and say, I'm going to get rid of these. They comment them out in the P4 program, literally comment it out, add a comment to the ones they don't want, and then they compile it down to the ones that they do. This has a few benefits. The first thing is you're not going to have a network fail because of a protocol you're not using, because it's not there. Little known secret, many data center outages are caused by a protocol that's running in a fixed function chip that they didn't even realize was running and for which they had no expertise to fix. So it's a liability sitting waiting to go wrong. It's also consuming resources, table space and power, that you could more usefully use for the features that you are using. So if you get rid of that, then you can liberate the space and use it for the features that you are using. Make tables bigger. You could take IPv4 tables instead of being limited to, say, 100 or 150,000 entries, make them 1 million if that's what you need in that particular environment. So I would take that program, I would modify it, let me call it myswitch.p4, and then I would compile it, and then that would be program the chip. How else is it used? Well, another one, of course, would be to add new features, proprietary features that I want in my network. You might think that surely I don't need that many. If I was to draw a protocol picture of 20 years ago, it would look like this, right? Ethernet, IPv4, and IPX. It has changed over time. So if I look at that equivalent graph for that switch.p4 program, it looks like this. You can't read it. That's just because it's so complicated. Even if you zoom in, then it's still quite complicated. It's not surprising that most fixed function switching chips have bugs in them, because it's really, really hard to get this right. In this case, it's a program, and so you keep iterating until it's correct, or removing the ones that you don't need if they're too complex. Each of those protocols, though, to be fair, was added by somebody that needed it. in these cycles of 4 years as they were added to the chips. The sorts of things that people we've seen add in addition to these: new encapsulations and tunnels. For example, segment routing of various flavors based on IPv6 or MPLS, etc. New ways to tag packets that they require special treatment. For example, distinguishing different types of traffic in a virtualized data center. New approaches to routing. I've seen someone build a data center with source routing. Just say, these are the sequence of egress points to the switches. If they want to do that, that's fine. They weren't able to do that before because the fixed functions didn't allow them to do it. Now they can build a network that's significantly simpler and cheaper. New approaches to congestion control. Think about what congestion control is doing. It's trying to identify where congestion takes place. Congestion takes place in switches. The switch knows the queue occupancy. That is the congestion. So why don't you tell the end host? Well, just tag the packet with the current congestion so that the end host can react accordingly. You can end up with far better, far simpler, far more reactive congestion control algorithms that are tailored to a particular environment. Why haven't we done this? Because congestion control was dictated by software people who were thinking about the end host, because they knew that the forwarding behavior was determined by chip designers, not by people that operate networks. So as soon as, this is a great example, as soon as you give software developers in networking companies the opportunity to change the behavior, then they will give themselves visibility into something that has been denied them in the past. And so this is a great example. New ways to process packets, for example, splitting up packets as they go through a switch based on the ticker symbols that are carried in the packets in order you can do a higher frequency processing of them. Probably can't guess what industry is interested in that. Other applications that we've seen that, frankly, took us a bit by surprise were ones where people wanted to take things that traditionally you don't think of being in the network and fold it into the network. So, for example, load balancing. There's a layer 4 load balancing example downstairs. This is not just forwarding based on forwarding tables. This is stateful load balancing, maintaining up to 10 million consistent connections at a time, and being able to replace hundreds of servers with a single switch, essentially folding all of that expensive server behavior into a top-of-rack switch, into the plumbing in the network. Another one is building very fast stateless firewalls that are able to take the addition of hundreds of thousands of new entries per second. So this kind of application, I mean, the interesting thing here is not the ones that I can come up with. That's what fixed function is. The interesting thing here is the ones that you can come up with. That's what programming is. Right? Putting it into software to allow others to put their ideas into the network. But by far the most interesting one so far has been network telemetry. And some of you have probably seen examples of this. You've probably heard about in-band network telemetry. In-band network telemetry was first deployed using P4. In fact, there is a program, int.p4, which you're welcome to use in your environment too. I want to explain a little bit of the background here. You may have heard me talk before, and in which case I probably complained about the way that we debug our networks. And I've been saying for maybe 10 years the same thing, which is for the previous 20 years, as far as I could tell, the only things and the only tools that we used for debugging our networks were traceroute, ping, and SNMP. In the meantime, our friends in compute and storage have developed hundreds and thousands of new ways to keep their systems working. It's not surprising that we always get the blame when something goes wrong. We have no idea how to fix it. So why is it that the switches and routers that we have in our network don't tell us what's going on? And I would say again, it's because they're designed by people who don't operate big networks. Their behavior is determined by people who don't quite know what to put in there. So what we've observed that people wanted to put into a programmable device seemed to fall into answering 4 very simple questions. Excuse me, I've just broken the I've just broken the system. Okay, there you go. That was clever. I drop it on the floor and it goes blank. Okay, my apologies. So take this network here. I'm going to take it down to a little bit simpler, and there are some green packets flowing in this network. If there is a packet in the network, why is it that I can't go to one of those packets and ask that packet, how did you get here? Which path did you take? I don't mean which path did a traceroute probe take that isn't this packet? Which path did this packet take? Why can't I just ask it? It took a particular path, so why doesn't it tell me that? Why can't it just tell me I visited these switches at this time? Why don't we take this as a given? I don't know of a single network in the world that can do this today. The second one is not only how did I get here, but why did it get here? What is the set of rules that it followed in each of the switches in order to get here? In other words, why can't it tell me that in each switch it followed a particular set of rules so that I can figure out why it's here so that if it shouldn't be here, I know what went wrong? I don't know of any network in the world for which you can do this. If there is something wrong from a performance point of view, how can I figure out how long it waited at each queue along the way? In other words, the delay that it experienced in each of those switches. You can see here one I've highlighted in red because it's too big. I want to be able to go to the switch and say, give me the time series of the occupancy of the queue so that I can see when that congestion took place. It's pretty obvious as soon as I look at the time series. I don't know of a single switch that can give you this detail or a single packet that can give you this information today in an operating network. The next thing I want to know is whose fault is it? How do I go and fix this? So whose packets did I share the queue with at the time of congestion? The green one at the bottom is me. I wasn't doing anything wrong. Who's the orange guy? I want to go and figure out who the orange one is. It's some kind of aggressor flow. If I can see the packets, then I can go and figure out how to go and fix it. I don't know of any network in the world where you can answer these two questions this way today. It's really strange that we expect networks to work when we can't answer any of these four questions. What path did my packet take? Which rules did my packet follow? How long did it queue at each switch? And who did it share the queues with? So I take these as four ground truths that you must be able to answer. The reason that Tofino with P4 can do this is because of this program int.p4 will answer all of four of those questions for the first time at full line rate without generating any additional packets in the network. I'll tell you how it works. It's actually very simple. And when you look at it, you'd be surprised that we haven't done this a long time ago. Packets arriving into the network, they are unchanged by the end host. When they get to the first switch, you just add in all of the information that you need in order to answer the questions. The queue, the switch ID, the rules that you matched upon, any information that the switch has, you can tap it into the packet in any location that you want so that it will fit with the protocols that exist in the network. I've seen this put into about 10 different locations, but it's actually under the control of the user by just changing the P4 program and saying, I want it here. So this gets tagged onto the packet as it goes through. There is a little bit of a danger that this is going to end up at the end host and then break the protocols on the end host. So typically, the last switch will then remove it and send it off to a log analyze and replay that can then visualize it so you can see what's going on. And then you're left with the original packet going to the end host. So the end hosts don't know that this is taking place. There are many ways that you could do this. As I said, this is a program. If you want to change and modify it slightly, then you're free to do so by changing a P4 program. This is the snippet of a P4 program that does that insertion. If I was to leave that program with you, you'd probably be able to understand it in less than 10 minutes. Right? So this is really designed to make it easy to do this. And if you wanted to place it in a different location in the packet, you could probably figure that out in about half an hour. This is a picture of a system that we built in order to be able to look at this and to be able to view this. This is a network with a hierarchy of 4 switches. This was just one put together in the lab. This was with hardware switches put together. The red one in the middle was experiencing congestion, so we wanted to take a closer look. This is the time series of the occupancy of the queues. Notice that the gradients here, the tick marks along the bottom are in 100 microseconds. And this is indicating at each instance which packets from which flows were in the queue at that time. So it's the time series of the occupancy of the queue. If that's too coarse a granularity, we can go in one step further. Now they're at 20 microseconds. And in fact, you can go to a granularity of less than a nanosecond and absolutely be able to see what was the occupancy. You cannot create a microburst that you don't see because you're capturing every single event. Once you've got the ground truth, there's nothing to worry about. Let me get back to the original topic. Now I've given you a sort of a flavor of what the power of that P4 programming language is. And this was the P4 runtime API. So the way that a user would typically do this, they would start with a program like tor.p4, which explains the forwarding behavior that they want. And then they would compile that to generate the data model used by the API. It's not quite true to say it auto-generates the API. The API stays unchanged. We're adding a data model to that API to extend and enhance it. And then the program derives a configuration to tell the switch what the pipeline is in the way I described earlier. So that's the kind of the process and the sequence of operations. So returning to our challenge, can we design an open, silicon-independent API? Okay, thank you. API that is easily enhanced as we evolve the forwarding plane. And the way that this will work, imagine I want to add an additional table, like say IPv6. If I was adding an IPv6 table to that, I would update the chip. I would add the new data model to add and delete entries to that table into the P4 runtime API. The good thing about this is the API has been enhanced. The API doesn't change. The control plane does not need to be rebooted. Only the switch may need to change, depending on the switch. And in most cases, you should expect that the chip forwarding behavior should be able to change and all of the tables downloaded in a handful of milliseconds. So the biggest interruption of service would be just a few milliseconds. So now we have an interface that's open and extensible, silicon independent, and can be extended without even restarting the control plane. In slightly more detail, I'll be quick because of time. On the left is the description of the forwarding behavior. That's the P4 program. And on the right would be normally the kind of runtime updates we might do to add or delete entries. The compiler will generate through something that Jim Wanderer described the other day, P4 info. P4 info comes from the program on the left in order to generate the data model used in the protobuf on the right-hand side. That is added to and extends the API. So now that protobuf format has been used to enhance that API between the control plane and the forwarding plane. That works equally well if the control plane is inside the switch, because you just use the same API as you did before. You may not need gRPC, you may simplify that, but it works in exactly the same way. You can extend it, enhance it as you need, without having to reboot the control plane when you change the forwarding behavior. So in summary, to wrap up, existing APIs are hidden. They're hidden behind NDAs and licensing agreements, or they're very hard to extend. Changing the API typically requires a huge amount of work and a major interruption of service. The P4 runtime API is designed to be easy to extend by its very nature. It's derived from the program that describes the forwarding behavior as it should be. The P4 runtime API can be used equally well by a remote or a local control plane, and the control plane doesn't even need to be interrupted when the API is enhanced. Thank you.